Welcome back to the class on a power semiconductor track. In this class, we are going to discuss about the second quadrant operation of the DC shunt motor, which is fed by the DC to DC converter. Another name for this is the regenerative braking also. In case of regenerative braking, armature of a DC motor is giving the power back to the supply. That is possible only the voltage across the armature is greater than the supply voltage. Suppose the armature voltage is less than the supply voltage. How we are making that voltage is more than the supply voltage, that we are going to see. Then only it gives the second quadrant operation. Second quadrant operation is nothing but the voltage is positive whereas the current is negative. So product of the voltage and current, the load power becomes a negative. So the armature of a DC motor is giving a power back to the supply. So whenever this armature of a DC motor is giving a power back, means the speed of the motor will be decreases. So this is the circuit diagram, this is the armature, this is the inductance. Actually, this is the inductance of a armature winding that we have shown separate outside. If that inductance is lesser, then we have to add some more inductance to the armature. By the time it becomes a external inductance also. So this is the control switch. Whenever you apply the voltage to the switch is closed, otherwise open. This is the diode, this is the supply, this is the positive direction of the load current, this is the positive direction of the source current. The current is passing through the motor, then we have taken is a positive. Now we are going to see the operation of the circuit. There are two modes of operation. First one is the switch is closed. When the switch is closed, this armature is consisting of back EMF. So due to that back EMF, the current is passing through the inductor and the switch again passing through the same motor. In this interval, the current is changing from the minimum value to the maximum value. The actual current is opposite to the reference. So whenever we are open the switch, the back EMF plus the voltage across the inductor is more than the supply voltage. So the diode is on. Now this motor is giving the power back to the supply. That is happen only when the VA voltage is more than the supply voltage. See, there is a difference between the VA and V. VA voltage before the switch, V is nothing but after the switch. These two are equal when the diode is on. Now we are going to develop the waveform. Initially, we have taken the y-axis, and the x-axis we have taken the t. So, taken this is the on time of the switch. This is the off time of the switch. This interval is nothing but the off time of the switch. This is the one cyclic operation. Same manner we are showing the one more cyclic operation. When the switch is on, the inductor current is changing from the minimum value to the maximum value. That we have drawn here because the actual current is opposite to the reference. So it is changing from minimum value to the maximum. When the switch is off, the diode is forward bias. Now the current is passing in this manner. Motor, inductor, supply, and return to the motor. So in this interval, whatever the energy stored in the inductance that given back to the supply. In this interval, the inductor current will be changing from the maximum to the minimum. Again, here this is on state. Once it is on, again the current will be changing from minimum value to the maximum value. Off, again the current is changing from the maximum to the minimum. If we observe this current waveform is drawn in the negative below the x-axis. So this current is nothing but a negative current. If you find the average value for this one, you are getting. Now we are going to see what is the voltage appearing across the supply. When switch is closed, the VA voltage becomes a 0. When switch is off, the voltage VA, this voltage is equal to the back EMF plus the voltage across the inductor. That is equal to VA. That voltage will be applied to the supply. This is nothing but a V. In the same manner, when the switch is on, 0. Because this voltage is 0. Again, on, this is equal to this. This is the voltage waveform for the V. To find the average output voltage, this is one cyclic operation. This is second cycle. This is the T. From this point to this point, the T. The area of the repeated curve. This is a repeated curve. This is off time. So T off into V divided by 2, that is equal to V, average output voltage. So the average output voltage is equal to V into T off divided by T. T off we can write it as T minus T on. So this is equal to V into 1 minus delta. This is equal to VA. Now we are going to find out the voltage appearing at this point, that is equal to V equal to VA by 1 minus. See, the voltage at this point and this point, the switch is there. This is only controlling how much voltage should be applied to the circuit, where delta equal to T on by. Now we are going to see variation of the output voltage versus the duty cycle. Already we know the output voltage, that is V equal to VA by 1 minus delta. Here we have taken one table. When T on is 0, delta equal to 0, the output voltage is equal to VA. Substitute here. When T on equal to half of the time period, then the delta equal to 0.5, then the output voltage is 2 VA. When T on equal to T, delta equal to 1, substitute here, output voltage equal to infinity. Now if we take on the x-axis delta and the y-axis output voltage, when duty cycle is 0, the output voltage becomes a VA, nothing but that point we are coming here. And the duty cycle is 0.5, the output voltage becomes a 2 VA, nothing but this second point we are getting here. And the duty cycle is 1, then the output voltage goes to the. So in this manner we are getting the variational output voltage versus the duty cycle. If we observe over the range of the duty cycle, the output voltage is always greater than the input voltage. That's why we're calling this, which is a boost converter. The speed torque characteristics of a DC shunt motor with a DC DC converter during the regenerative brake. We know the general expression for the speed torque relation. Omega equal to V by K minus IA by RA by K. Armature voltage equal to, already we derived the expression V equal to VA by 1 minus delta armature voltage, that is output voltage. This is equal to V equal to VA by 1 minus delta, where T equal to minus of K into IA, because in regenerative braking the current is opposite to the motor current. So that's why here we have taken the minus. Now in place of IA, you substitute the minus T by K. Then we are getting in place of V, you substitute the VA by 1 minus delta. Then the speed of the motor becomes a VA by 1 minus delta into K plus T into RA by K square. This is the speed torque characteristics of a DC shunt motor during the regenerative brake. Now, how we are going to represent this in a graph mean? On the x-axis you have to take the torque, and the y-axis you have to take the speed. As the delta is changing, these are the different speed torque characteristics of a DC shunt motor during the regenerative brake. As the delta is increases, the curves will be shifted upwards. Moreover, one more point what you have observed here, all these characteristics we have drawn on the negative of the torque, where the speed is so the power becomes a negative, so it gives a regenerative brake. Class we have discussed about the regenerative braking of a DC motor, nothing but a second quadrant operation of a DC shunt motor by using a DC to DC converter. Next, we will derive the expression of the output voltage. We have seen the speed torque characteristics of a DC shunt motor during the regenerative braking also. Thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of the YouTube channel, so that I am always available to answer all your